When you hear the term heart failure, you probably imagine a simple mechanical breakdown, right? Like a car engine just giving out. But it's so much more complicated than that. It's a fascinating and honestly a tragic story of the body's own survival instincts going horribly wrong. It's about how its desperate attempt to fix a problem becomes the very thing that destroys it.
And this isn't some rare, obscure condition. The consequences are absolutely devastating. In the United States alone, heart failure is a contributing factor in nearly 400,000 deaths every single year. That number is just staggering, and it really highlights why it is so critical to understand what is actually happening inside the body. So here's our roadmap for this explainer. We're going to start with the overworked pump itself. Then we'll look at the body's incredible emergency response. After that, we'll see how that response leads to even bigger problems. We'll break down the two main ways a heart can fail, a squeeze versus a fill problem. Then we'll see how the two sides of the heart are connected in a kind of domino effect. And finally, we'll explore the ripple effect that spreads throughout the entire body.
Okay, so let's set the stage. At the very beginning of this whole story is a simple, relentless problem. The heart is being forced to do way too much work for way too long. So what is heart failure really? Well, at its core, the definition is pretty straightforward. It's a state where the heart, our body's tireless engine, just can't pump enough blood to keep up with what our body needs to function. It's either become too weak to push the blood out, or it can only get the job done by creating dangerously high pressures inside its own walls. Now, this kind of failure almost never happens out of the blue. It's usually the final, brutal chapter for a whole host of chronic diseases. Think of these as the long-term villains of our story. Things like high blood pressure, which makes the heart fight against insane resistance 24/7. Or faulty valves that cause it to work way harder just to move the same amount of blood. And of course, ischemic heart disease or the scarring from a past heart attack. They all put this relentless, crushing workload on the heart muscle, day in and day out.
But here's the amazing part. Faced with this crisis, your body doesn't just throw in the towel. No way. It kicks into survival mode, activating these powerful, ancient mechanisms in what you could call a truly heroic effort to keep the system online. So, what does this emergency response look like? Well, first, the body calls on something called the Frank-Starling mechanism. Basically, the heart muscle stretches out more so it can snap back with a more forceful contraction, kind of like pulling a rubber band back farther to get a more powerful shot. Then it floods the system with hormones like norepinephrine to make the heart beat faster and stronger. It also fires up the RAAS system, which tells the kidneys to hold on to salt and water, beefing up the total blood volume. And finally, the heart muscle cells themselves actually start to get bigger. It's a process called hypertrophy.
But this is where the story takes its tragic twist. That primary solution, making the heart bigger and stronger, ends up becoming the new and frankly a far more dangerous problem.
See, it turns out not all heart growth is created equal. The kind of bigger heart you get from exercise, that's physiologic hypertrophy, and it's great. It comes with new blood vessels to support the new muscle, and it makes the heart more efficient. But the kind you get from disease, that's pathologic hypertrophy, and it's a disaster. The blood supply can't keep up with the new muscle, stiff fibrous tissue starts to get deposited, and the overgrown cells become incredibly fragile and super vulnerable to any drop in oxygen. And this isn't just theory. You can literally see it under a microscope. On the left, you've got these nice, neat, organized heart muscle cells. That's a healthy heart. But look at the right. Those are hypertrophied cells from a failing heart. They are enormous, they're jumbled, they're disorganized. This is the picture of a cellular system in complete crisis. And if we zoom out from the cells to the organ itself, the changes are just as stark. That heart in the middle, that's a normal heart. Now look to the left. That's a heart that's been battling high blood pressure. Its walls have gotten incredibly thick, which actually shrinks the space inside. And on the right, we see a different pattern of failure, where the whole heart has become stretched out and dilated. In both cases, the heart has been remodeled into a weaker, less effective version of its old self. This physical remodeling, this change in shape and size, it leads us to two main ways the heart can fail. It's not just one single issue. You can think of it as either a problem with squeezing blood out or a problem with filling up with blood in the first place. Okay, so let's break that down. On one hand, you have systolic failure. This is a squeeze problem. The heart muscle is just too weak to pump blood out effectively. We measure this with something called ejection fraction. And here, it's low. But then there's diastolic failure.
This is a fill problem. The heart muscle has gotten so thick and stiff that it can't relax enough to properly fill with blood between beats. Now, the crazy part is, the ejection fraction might look totally normal, but the heart is still failing because it's not taking in enough blood to begin with. Now, here's something you have to remember. The cardiovascular system is a closed loop. The left and right sides of the heart are working together, so a failure on one side rarely stays on that one side. It creates a chain reaction, a domino effect that's almost inevitable. So the trouble usually starts on the left side of the heart. This is the real powerhouse, right? It's responsible for pumping oxygenated blood to the entire body. When it starts to fail, it can't keep up, and it can't pump out all the blood that's coming in from the lungs. So what happens? Pressure builds, and fluid starts to back up, right into the lungs. This is what causes those classic awful symptoms of breathlessness, coughing, and what we call pulmonary edema or wet lungs.
And all that backed up pressure in the lungs, well, it doesn't just stay put. It creates a massive traffic jam that the right side of the heart now has to try and push against. And over time, the right side of the heart, which is really only designed for low-pressure work, just gets completely overwhelmed. It starts to fail too. And now the backup isn't in the lungs anymore, it's in the entire rest of the body's venous system. Fluid starts to leak out into the surrounding tissues. This is what causes the swollen legs and ankles, a congested and enlarged liver, which can get an appearance they call a nutmeg liver, and even fluid building up in the abdomen. And this is the point where the name congestive heart failure becomes tragically, painfully clear. The failure of this one pump creates a state of congestion and dysfunction that ripples through the entire body. Absolutely no organ system gets off easy. The lungs, they usually take the first hit. But it doesn't take long for the liver, the kidneys, and even the brain to come under immense strain, both from all the fluid backup and from the simple lack of fresh oxygenated blood. And the specific damage is really severe. In the kidneys, for example, that reduced blood flow actually triggers them to hold on to more fluid, making the whole situation even worse. In the liver, that chronic congestion can lead to permanent scarring. And in the brain, a chronic lack of oxygen can lead to confusion, irritability, a condition we call hypoxic encephalopathy. This quote from the source material really just hits the nail on the head. It perfectly sums up the whole tragic process. The cardiovascular system is a closed circuit. There's no escape valve. Failure on one side will produce excessive strain on the other, and it all ends in global heart failure. Which really leaves us with this one final, profound question. The body's entire response to a struggling heart, to work harder, to get bigger, to hold on to more fluid, all of it makes perfect sense from a survival perspective. It's a desperate, logical attempt to stay alive. But in the long-term setting of heart disease, that very programming becomes a self-destructive spiral. It's a tragic paradox, right at the very center of our own biology.